Welcome, everybody. We'll give another minute or so for people to jump in. Right now, we've got a little over 30 people joined, so it should be a good session. Looking forward to what comes out of this. As it is 12 o'clock, we'll go ahead and get started here. Again, like I said, we appreciate everybody joining in and participating in this discussion. This is Lauren Stowe from VTTI. I'll be doing the primary presentation, looking at the radar data, and then we'll have additional panelists discussing the use. In terms of what our plan is for the day, this is our agenda, so we'll take a moment and provide a brief introduction, and then I'll provide an overview of our data that we have available, how it was collected, and then what we did to it to try and make it more usable for researchers. And then I'd like to take a moment and let our two additional presenters give a brief introduction for themselves now, so that you have an idea of who you'll get the chance to hear. So Hao and James, if you could go ahead and take a moment and introduce yourselves before we get started. Hao, why don't you go ahead and start?
Hello.
Yes.
Lauren, can you hear me?
Yes.
Okay. Yes, this is Hao Xu from University of Nevada, Reno. I'm an assistant professor there and have been working on several projects by using the new SHARP2 NDS data.
Great, thank you. James, give a little background for yourself.
Hi, everyone. My name is James McGarry-Otis. I'm a mechanical engineering student at Drexel University, and I'm also a researcher here at the Center for Injury Research and Prevention at the Children's Hospital of Philadelphia. We've been working with the SHARP2 radar data for a bit, comparing teen and adult driving behaviors, so it's been pretty useful to us here.
Excellent. I had initially planned on letting people provide a brief introduction for those that were in attendance. However, currently we have 45 people signed into this, so for the sake of time, we will forego that. But again, thank you for joining in. So we'll go ahead and jump in. We should have 15 to 20 minutes at the end for question and answer. If you want to type in questions that are, you can use the box, the Q&A box that's available through the WebEx. If you have a quick clarifying question as we are presenting, jump in and ask it if you would like. Again, we want to keep the discussion flowing so everybody has time to get through all the content and everybody has that available to them. But if there is something that is not clear, go ahead and ask. If it makes sense, we'll push it off to the end. But otherwise, let's go ahead and get started. So in terms of SHARP data, kind of an overview, what I will be talking about is giving you a brief description of what we collected, Before that, I want to provide just a little bit of content as to how radar data is collected, as that influences people's understanding of the data that we actually have, and then talk some about the specifics of the SHARP-2 data itself. So radar 101, in the most simplest form, it's analogous to a BATS echolocation, where a transmitter sends out an electromagnetic wave. It bounces off an object. That object, the signature of that object is received back by the antenna. The timing of those waves in terms of the sending and receiving is accurately measured, and then through that, that object is then detected within the signal. For the application of collecting the data off of a vehicle, that information is processed in real time. So as those signals get returned, there are a lot of different bits of information there. So you can have multiple signals coming off of a single target, and how those data are grouped into and combined to say all of these returns are a single target has to be done in that real-time processing. So it gets the signals, groups those into candidate targets, and then the targets from that time and slice are assigned to existing targets if it makes sense within the construct of the algorithms that are designed to track the different objects and targets. If it doesn't, if an object returned signal from an object doesn't fit in given the constraints of the algorithm, then a new track is created for that object. Once those objects or those targets are assigned to tracks, then there's an additional algorithm that essentially connects the dots to say, hey, this one does go with the previous ones that we have, and from that information, then we can start looking at relative information to the host vehicle. In terms of how that actually looks, this here is an example of a radar return, a raw signal. It's a slightly different antenna type than what was used in SHARP-2, but it is the same company, and this is one that they make publicly available. If you want to see it in real time, this is a screen capture from a YouTube video that they posted, which is somewhat interesting to watch the targets go by. But what you can see here is there are a lot of objects in the field of view that are showing up with very strong signatures, radar signatures, that have absolutely nothing to do with the driving experience itself. So you can see the building in the image on the right-hand side is creating a very strong signature. The little dotted line is the path of the vehicle, the host vehicle. So everything behind that are objects that it's already gone past, and everything in front is what it's seen. So you can see the little dotted line, and then the two vehicles that are in the image, the gray one on the left-hand side and the blue one on the right, those correspond to those first larger dots that are just in front of the end of that dotted line. So you can see kind of the challenge of processing in real time that the radar manufacturers have to identify what is truly a target and what's not. And the fact that they're doing it in real time, and we'll talk a little bit more about this, gives us an opportunity to improve some of those signals once we can look at it from a kind of an infinite perspective in terms of time to know what actually happened in the future with those signals. So the SHARP-2 radar, the one that was used, directly measures the range, the radial relative speed, and then the azimuth angle. So It knows the angle from the host vehicle to the target and how far away that is and how fast it is relative to that. That's important when we start looking at subsequent measures that get reported because they're derived measures. So for instance, the Y velocity, that is the lateral movement of a target relative, is a computed value. It's not directly measured. As discussed briefly, the data that are collected, that raw information that we were just looking at, it's stabilized and cleaned up through tracking algorithms. And one of the inputs to that is the host speed. So the vehicle that the radar is mounted on, as an input into the radar, provides the velocity of the host, and then that is used in the algorithms as well. The polar data that is returned from the radar gets transformed into Cartesian coordinates so that we can discuss variables in terms of X and Y relative to where the radar is located on the host vehicle. The radar itself, the raw data that's returned, is an object ID. So if there are 5, when you first turn the vehicle on, if there were 5 targets, we would get ID 0 through 4. And for each of those, you would get an X range rate, Y range, and a Y range rate for those objects. And then as you go and objects drop out and come back in, new objects come in, we continue to get that information. Talked briefly about some of the processing constraints for doing this in real time on the radar. We obviously have limited processing power compared to what we do for post-processing. In addition, there is limited time that the radar has to process that information because it's trying to capture it. The processing cycle for the radar that was used for SHARP-2 is 40 to 50 milliseconds. Obviously, post-processing, we can take however long we need to try and improve some of the quality of that data. I also mentioned the fact that it has a limited view of what temporally the data contains. So it can't look into the future as to what the targets are going to be doing. It only has now and what the past history of those data points. And then the last item there is the fact that if it made an error in a point that it called a new track, such as what happens when we get into a ghost target situation, it can't go back and fix the historic data that's already been sent out. That's already sent off, it's stored, and for posterity, or for our benefit of looking at it later. When we start post-processing, we can kind of get around all of those. The other influence on this is the fact that our data acquisition was designed to, with some specific features that were a systems engineering perspective beneficial for the study as a whole. So we are using a wireless connection between the radar and the head unit in order to be able to expedite the installation time. Consequently, there's delay in that when that data is collected, that data point is collected, and when it's actually stored. We timestamp it so we can correct it, but you'll see what the effect is. Also, vehicle speed is an important part of the algorithm. Initially, all the vehicles were using network speed. As the study went on, in order to improve the distribution, that was opened up to older vehicles that did not have network speed, in which case we use GPS speed, which is not as accurate in dynamic and low speed situations, and it's also not as a high sample rate. So with that, and I just wanted to spend a little bit extra time on that because people that I've talked to don't necessarily understand some of that background. And if you do, it provides an appreciation for what the radar manufacturer is trying to do, but then also what we were trying to do to help clean that up. So what did we do? First of all, we reorganized the data to make it more friendly. Data was sent down and stored in a way that was concise and compact. Time lag mentioned a little bit in the sending of that information, so to clean that up. Created objects that were consistent, so as objects come in and out, they can swap an object ID, so we linked all those together, and then we tried to smooth out the data, and then that was processing of the data in terms of fixing some of the erroneous signals. The big one is ghost targets, which we'll spend a little bit more time talking about, but it's essentially trying to make sure that targets that are not there don't show up in the data. And then we also tried to provide value for the researcher to provide information that made it easy to search and look at. So as we go through these items, and it'll be relatively quick, they're set up where there's a little bit of background information, the problem that we're trying to solve, and then the solution. So I already talked about the way that the object IDs were organized. There was a 8-bit counter, and as objects came in and out, that counter was incremented to make it unique for that time frame, a unique identifier. Obviously, that counter rolled over in order to collect more than 256 targets within a trip. We also worked with the manufacturer to try and make as compact of data packet as possible. So in post-processing, essentially what we're trying to do is make it easy for the researchers to look at that data. So the first thing we did is, here's an example of a trip, and you can see it gets up to 255, counter resets and continues. So the simplest thing is we just simply continued counting beyond this 255, which is why you get 400 plus targets. The problem, though, this is the easy part. I'm actually going to jump forward 3 slides. What ends up happening, though, is you get all these different colors, which, even though it's the same track, it's toggling different object IDs. So one of the other things we wanted to do was to link all of them to where the researcher didn't have to go through and do this themselves. So we reorganized the structure in order to make it easy for the researcher to go in and say, hey, I want to look at this particular object ID throughout its life with that host vehicle. I'll look at the picture because I think it's easier to view. So at a given timestamp, you can see that the primary target, according to the radar, was object number 4, this one directly in front. It saw target 5, but it threw it into track 1 because it wasn't the primary. And then there were additional targets in the future which aren't being seen in here. At the next timestamp, however, this vehicle is closer, so it gets the primary point of track 5, or pardon me, track 0. And track 4 gets slid over into the second object ID. At the next timestamp, this other vehicle has come into its primary point, so things get switched around as well. So what we did is we restructured the data so that at each timestamp we get this consistent presentation of data based on time rather than based on object ID, which is where you end up with this much cleaner looking graph. So that was the reorganization. The other thing that we did then was addressed the lags in time that occurred during the communications path. There is a possibility of delay depending on when the packet shows up and when it actually gets sent via Bluetooth. and then there's also latency within the transmission. And then, as note here, in some instances we were simply missing the radar timestamp. So what you end up with if you look at the DAS timestamp compared with the SMS, which is the radar manufacturer, when the data were collected, you get this offset. So essentially all we were doing was shifting it to where everything lines up. And just by doing this, we end up with a much cleaner looking signal, and all we've done is corrected for timestamp there. So if you end up looking at raw radar data, and this happened, and people originally looked at it and said, well, this data looks terrible. It's because we had a known and expected question of when that data were stored versus when it was collected. Once it's corrected for the collection time, it cleans up quite a bit. So in terms of a final example, you can see instead of having these horizontal jumps, particularly in the range data, all of a sudden everything starts looking a lot cleaner, and also in the Y range. Y range is a unique situation, but we'll talk about that here shortly. As far as the joining of the objects, again, as we talked about, at each step, the radar determines if an object that is returning a signal should correspond to an existing target that's being tracked. If not, it's provided a new ID. It does a pretty good job, but again, since it doesn't know what the future information is about that target, by being able to look at tracks in their entirety, both at a given time and in the future, we have a lot more benefit to be able to, and possibility to correctly connect them. So if you look at this example here, you can see from the X-range data, and it might be hard to see, you've got this green section which corresponds to the X-range rate, that green there. Fairly obvious that that should be part of it. So even though the algorithm in the real time didn't think that it should, we can go back and go, hey, you know what, that really should be. And so we linked those together. And that cleaned up a lot of the data, as well, as I'm sure you can see. Once we had all of these steps done, and these are presented kind of in the order in which we were looking at them, so give it a common ID, correct for time delay, connect all of those different segments that should have been a single object. Then we looked at smoothing some of the data. And the big reason for this is, or the primary influences were the sensor accuracy, but also the fact that what the radar is doing is going to inherently provide some noise in there. So the X, that range data, is an accurate measure. It's corresponds most closely to that radial distance that's being measured. However, as soon as you get a target off to the side of where the host is, then instead of having this nice flat back end of a vehicle, you can then have not only the back, but you can also have the side of the vehicle. So an object that has a length of several meters, if it can see the front quarter panel and the rear quarter panel, as well as the right rear portion of the vehicle, any of that can return a reflected signal from the radar. And it would obviously have different ranges along the, for that radial distance, which provides noise. Similarly, if you have a vehicle directly in front, that lateral offset could be from the left side of the vehicle or the right side of the vehicle, and it would be the correct information for the lateral offset for what the radar sees. It's not seeing a point, it's seeing the object as a whole. So an accurate offset would be anywhere plus minus the width of the vehicle. And of course, when you move that outside the lane, then you also have the length of the side of the vehicle that comes into play. Range rate for X, it's measured directly. For Y, however, it's a computed value. It's the time derivative, which is, since Y is the radius times the sine of the theta, the derivative of that is a function of r dot as well as theta dot. However, theta is relatively small. Based on the radar itself, it's plus minus 18 degrees is the range, so it's always going to be less than 18. So right there, that r dot only is accounts for approximately 30% of the y dot. For vehicles that are far in front, it's more like 2 to 4%. However, the radar can't measure theta dot directly. Therefore, the simplifying assumption is made that it's only a function of r dot and theta. Consequently, the y dot is suspect at times, which if you look at the raw data becomes obvious. So what we did there is we used cubic splines to fit the data as a whole, the different parts of it, in order to be able to clean things up, but yet still maintain the dynamic representation of what actually was occurring between the vehicles. One of the things that we did is get rid of, you can see in the red circled area, get rid of physically impossible events. Obviously, the Y cannot physically jump within 1 or 2 timestamps several meters. So by using the algorithm that we did, we go from this, which is obviously physically impossible, to this, which is much more reasonable behavior of the vehicles. Once we had all the data cleaned up, then we started looking at identification of ghost targets. And ghost targets are primarily a function of, again, the way that the tracking algorithm is done. And what happens is, based on where the algorithm expects a target to be, if there's a significant dynamic change in either the host or the vehicle, the object that's being measured, if the object is not where the algorithm expects it to be, it'll hold that point and then look at the next time slice. Consequently, if that continues to propagate, what ends up happening is you get the object being held in artificially in a point in time and a place in time. As the vehicle starts to pull forward, you end up seeing an object that's not actually there, which is what we see here. Vehicle are stopped at stop sign or stoplight, light changes, vehicle pulls away. The algorithm doesn't capture that. So this target here from that dot to there is a target that does not actually exist. It's one that's being artificially created in the algorithm. But you can see here, the correct target is picked up, assigned a different ID, and it continues forward. So that is one example. Another is if that we tried to capture here that we classified as ghost targets is if it picks up a stationary object. There's a filter that takes care of most of that, but it doesn't always do that. So by identifying those, we were able to clip this portion and connect those tracks and eliminate a lot of these targets that are just that, they're ghosts, they don't really exist. The last thing we did to try and improve the usability is we added some additional variables. So lane classifier, lead vehicle indication, and then direction of travel and headway. So for this, we assigned lane positions and classified those based on the lateral offset. We also took into account curvature, which we can do since we know the path of the vehicle. We also then identified lead vehicles, and after the parsing of the lanes were done, to provide that as a sorting, something that researchers can sort against as well. And then we restructured the data so that things can be looked at by particular variables. So for instance, here you can look at targets based on lane position rather than having them just on a time-by-time basis with everything grouped together there. So from beginning to end, we started with this and ended up with this kind of information in the processed and presented data. In terms of lane relative to host, we took into account where the lane changes were occurring by the lead vehicle, so you get a consistent measure of that lane 0. So if the host moves versus the target, that's accounted for in those lane classifiers as well. And then finally, the data that are available. This is the reorganized data plus the additional processed data. So that's our raw data, and that's processed data that are available for researchers. And with that, I'm going to hand the ball off to Hao and let him discuss his example of how he's used the data. So Hao, you should have the ball if you want to start presenting. Oh, I think you're still muted there.
Hi, Lauren. Hello.
Yes, go ahead. You've got the ball, so
yeah.
You can.
Could you read my screen now?
I'm not seeing your screen yet. So if you, you'll still have to share your. Should you go to the Quick Start tab?
Okay, I got that. Okay.
All right, it's coming up now.
Okay, great. So we have used the SHARP2 NDS radar data for our driving cycle development. So in today's short presentation, I'm going to share the study background and how we use the NDS radar data to serve our research, and briefly report the results and also summary of our experience. So driving cycle, basically it is representative vehicle speed and the time profiles under different highway and traffic conditions. So normally it's widely used for fuel consumption estimation. We also apply the driving cycle information for traffic safety analysis or traffic operation evaluation, like a control delay or car following. A typical driving cycle is just like the chart shown on this slide. So the research objective is to develop new and more driving cycles by using the large SHARP2 NDS data set and also the RID data. So for our research, we would like to study the driving cycles not only for passenger cars. We also want to learn the large light-duty vehicles, buses, small single-unit trucks, and even combination trucks. But the chart, this slide shows the distribution of vehicle types of NDS data. So we can see the car, SUV, crossover, and van or minivan. Clarify them as small duty vehicles. So pickup truck is only 5.6% large light duty vehicles. So I just colored the different types of vehicles. So small light-duty vehicles, we have a great data set for driving cycle development. So large light-duty vehicles very small, but for buses, single-unit trucks, we do not have any data directly from the time series record of NDS data set. So then we found we can extract some information or additional data from the leading vehicles. The idea is based on the available radar data and also front videos. So the right screenshot is a front video picture, and we know NDS vehicle was equipped with GPS sensor, front cameras, and the radar sensor. So when we have a leading vehicle, if it's no matter the truck or bus or competition truck, we can know the distance and the relative speed between the NDS vehicle and this unknown vehicle. And by the camera, we can identify the vehicle types. In this way, we can get a bunch of speed information of the leading vehicles, and absolutely we can get the vehicle type through the video. So we just use the very basic radar data, the range X, range Y, the distance, and the relative speed, just as what Lauren introduced. So when we use the radar data, we also filter the data set based on our project requirement. First, we only want the records with a validate radar ID. That means there is something in front, some leading vehicles. And also the minimum, the radar range, we use the range between 0 and 300 feet, because when we use the data, we feel the radar distance accuracy in this range is we have more confidence. And also we have a cover period longer than 10 seconds. That means we want the car following behavior is lasted longer than 10 seconds. This can remove or exclude some random errors or noise or other situation. So by end, we have a list of the trip segments extracted based on the radar data and based on the filtering algorithm. So then we need to connect the vehicle type and also the radar data. Then we can know for different vehicle types what is the location. We found the process is very time consuming to recognize the leading vehicle type. Because the time series files, time series data records and radar data and videos are in different files. So originally, our students need to first check the timestamp in a radar file or time series record, and then open the video file to find the timestamp to identify the vehicle types. If there is connection between the time series record and also the video frames. And also we have the file ID to connect the file and the time series file. So based on those information, the time step. So we also developed one semi-automatic vehicle type identification tool. So we connect the videos and the identified radar records. So then one by one, this tool can automatically show the right frame for the related radar records. So then the student can basically click the button next, then we will see the next vehicle picture and can input the vehicle type. So in our project, we originally used 400 trips. Then we found that was not enough for our study. So we requested and received additional 4,000 trips. So those trips were collected in the 6 sites and both rural and urban area. For the leading vehicle data extraction procedure, by end we get the data as listed in this table, extracted leading vehicle trips. So for different vehicle types, we have the different trip number and the different record numbers. So we have a very good good numbers for small light-duty vehicles and large light-duty vehicles. But for buses, small single unit trucks, and combination trucks, we found the records around. So we have a good number of records here, but in our study, the percentage of those numbers are pretty low. Like buses only 0.4%, combination trucks 1.6%. So in fact, these percentage numbers, they are consistent with the national vehicle mileage travel. So we checked 2013 and 2014 miles traveled by the different vehicle types. We found the bus only counted about 0.5%, and the single unit trucks counts 3.6%. So the low numbers of bus truck trips they were caused by distribution of the miles traveled. So with these bus records and bus or truck trips, we can develop some driving cycles, but it cannot cover all the scenarios, all the road conditions we expected. So we applied some other approach to fill all the gaps. The leading vehicle information did give us very good information about the other vehicle speed information. In our project, we also requested and used the raw radar data. So one major difference between the processed radar data and the raw data is the number of objects or targets. In processed radar data, we received the original data set about 1 year ago. So we found for each record, we only have one leading vehicle in that record. But when we receive the raw radar data, we can get all the leading targets information, the X, Y distance, X, Y speed. So here's a summary of our experience of using the NDS radar data. The radar data is important for describing the traffic conditions. So it can give us the leading vehicle speed location information. It can also help us to understand the traffic congestion, like the level of service. And also we found the combination of the radar data and from the videos. If we extract the data information from the integration of radar data and from videos, we can dramatically extend the current time series data set. And also the NDS data set is huge, but the data may be limited for a specific situation, like a specific road condition, specific traffic condition, or vehicle type. And also our limitation may be caused by our received data set. We only used 4,400 trips. That's limited by our budget. We cannot get all the NDS data set. So I think if we can, if the NDS data set can be processed, we may get more trip information, speed information about the vehicle types. And also the raw radar data may provide additional information, but definitely it costs us a bunch of time to understand the details to smooth the data. And by end, I would like to thank the support from VTTI. So every time when we had questions or requests, we received very prompt responses. And also we received a great suggestion for data requests and the data processing, and also additional information for understanding the data set, like data dictionary and some documents. We very appreciate all the help. Yeah, that's all my report. Thank you, Laurie.
Thanks, I appreciate it very much. James, I'll pull the ball over to you. I think I will. See if I can do this. Joel, you might have to pull that over to James. Or James, you might be able to grab the ball also from Hao and pull it over there.
Okay. Yeah, no, it doesn't look like I'm able to do that.
Okay. Okay, Joel, you might have to send that over there. Joel, can you grab that and send it over?
Okay, I'm the presenter now.
Oh, great, great. Perfect. Thanks, Joel. Go ahead, James. Thanks.
Okay, hi everyone. Once again, I'm James McGarry-Otis. I'm a mechanical engineering student at Drexel University. I work here at the Center for Injury Research and Prevention at the Children's Hospital of Philadelphia. And we've been working on a project for analyzing SHARP-2 data to compare teen and adult driving behaviors. I've been working under Dr. Helen Lowe, and I'm just going to tell you a little bit about the project itself, what we've been doing. Once again, we're comparing adult driving behaviors using the Naturalistic Driving Database. We've been looking at crashes and near crashes. Most of the time in these, we're only looking at short portions of the radar data or individual timestamps, and we're interested in computing the TTC at braking to gauge the difference in reactions between the teen and adult drivers. Now, we're also beginning to work on baseline driving analysis, where we identify instances of steady state car following conditions and utilize the radar data in order to provide unique driver behaviors that might be specific to either teen or adult drivers. I'm just going to tell you a little bit about how we processed and filtered the data. Most of the data was extracted from the CSV files using MATLAB. We looked at the lead vehicle radar data because most of our research involved areas where our subject vehicle was following the lead vehicle. We looked at rear-end crashes, rear-end near crashes, and instances of car following. So we did encounter a few problems with missing lead vehicle track indicators, as Lauren mentioned earlier, but so we filtered out the events with incomplete or missing radar data. But for crashes and near crashes, we only needed the radar data at the moment of braking because that's the only time we were really interested in. And we were able to identify the timestamp when the driver began braking using the acceleration data as kind of a surrogate, since the brake state data is when it's actually there, it's a low frequency. So that wasn't really accurate enough for the analysis we were trying to accomplish. But and also for baseline data, for baseline driving conditions, we needed continuous radar data for a minimum of 5 seconds. So some of the files with incomplete radar data were usable, some were not. But we were still able to extract many usable events. So I'm just going to tell you a little bit about what we've done for pre-crash analysis. Now this is looking at rear-end crash scenarios. And what we did was we looked at the TTC at the moment of braking to see if there's a significant difference between the time to collision at braking of teens and adults when there's an imminent collision. And as you can see, the TTC for teen drivers is considerably lower than adult drivers. Now, the statistical power of this test, when rear-end crash scenarios, we only had 5 adults, 4 of which had radar data. So, it's questionable how significant that is. But so moving on, we also looked at the radar data in near crashes. And what was interesting is while the TTC at braking for near crashes was nearly identical for teens and adults, we did find significant differences in the components used to calculate that variable, which is the headway distance and the relative velocity. And as you can see, the teens had a lower headway distance at the moment of braking, but also exhibited significantly lower relative velocity when they were braking. But which could explain the elevated crash rate among teens, because that headway distance, the larger headway distance exhibited by adults, provides a greater measure of safety since relative velocity is prone to very fast changes. So, that headway distance. Yeah, and just to clarify, there were 39 teen events that we were looking at, and I believe 5 adult near crash events. I'm going to tell you a little bit about the baseline driving analysis also. Our region of interest was steady state car following instances, which we defined as having a time headway of less than 4 seconds. Obviously there's a lead vehicle. We wanted the subject vehicle to have a velocity greater than 25 kilometers per hour. And we're also looking for events where, to be defined as steady state, we want the relative velocity to oscillate about 0 meters per second and converge. For the most part, they will converge on 0 meters per second if it's steady state car following. We also looked at the distance headway, which this is a characteristic of an individual driver, but it will oscillate about some comfortable following distance for the drivers. And what we wanted to see if, this following distance was significantly different for teens and adults. We also generated Wiedemann plots in order to better visualize some of this data. So I'm going to show you some of this. Now, this is just an example of what we observed for, a relatively standard adult car following instance. These plots are just used to help visualize the driver's behavior. The triangles represent, what we call perception thresholds, or the point at which the driver begins to respond to the visual stimuli. An adult driver tends to exhibit less frequent oscillations, but greater amplitude about that comfortable following point, which we talked about. You can see that from these time series plots over there. Delta X is oscillating around 19 meters. And delta V, once again, is oscillating around and converging on 0 meters per second. Now, if you take a look at what we tended to see for teens, teen drivers tend to exhibit more frequent oscillations, but smaller amplitude about this point, which in this instance was about 14 meters. But, as you can see, the delta V for these teens is fluctuating greatly, and so is the delta X. Now, we also looked at the TTC in baseline driving instances to see if we could notice any difference in teen drivers display consistently lower TTC values during steady state car following than adults. This is data from over 500 events and amounts to about 45 minutes of continuous driving data for each group, for teens and for each teen and adult group. Now, what we've recently started doing, you can actually use radar data to make predictions on future behavior from the driver. It's just a simple response stimulus model. This model is based on the GM car following model. It's been changed slightly in order to only use radar data from the SHARP2 data set. But so the driver's reaction to stimulus sometime, delta t into the future, which is a characteristic unique to the driver, can be approximated using the radar data and a few calibration constants, which are also unique to the individual driver. But as you can see, you're actually able to make a pretty reasonable approximation of how this driver will behave. And, we're predicting, I believe here it's 1.5 seconds into the future. So these predicted lines are actually based on the radar data from 1.5 seconds previous to that point on the graph. Some of the challenges that we encountered using the radar data, first of all, not all of the events had radar data, and some of the events with radar data did have periods of missing or invalid data. Missing lead vehicle tracks specifically posed a problem when extracting the radar data because it's there. I'd like to be able to use it, but without watching each individual video, there's no way to tell if this is due to a lane change or just a drop track on the lead vehicle. Another limitation was the 10 hertz sample rate. That was specifically for crashes and near crashes because these events happen very quickly, so our amount of accuracy was limited by the frequency of the sample rate. We have published a little bit on this SHARP2 data. We'll be at VTTI in August and also at AAAM over in September. I hope to see some of you there. Thank you for watching, everybody.
Thanks, James. Appreciate that. So with that concludes the presentation portion of it. We have seen one question come up regarding the FOT control speed versus network speed, and Miguel responded there. The difference, they're the same when the network speed is available. Otherwise, the FOT control speed is based on GPS speed. However, both GPS and network speed are in the data set when available and available to researchers. So, are there other questions that people have regarding anything that has been discussed so far? You can type them in. I'm not sure if everybody has audio capability, but also feel free to request it directly via audio. As we're waiting, I do want to again express my appreciation for James and Hao and their presentation and their use of the data and showing the variety of research that can be done with the data. It's really there's a wealth of information there that can be mined. Okay, I'm going to assume that silence means that we have covered everybody's questions. The recording will be available from this on the Insight website. So that should, as with the previous webinars that have been done, so those are there for perusal later. Well, again, thank you very much. We'll wrap up here 4 minutes early so you guys can grab a 4-minute lunch. And hang on just a second, there's one more question here. Question is, were you recording things for the drivers, what they were doing, such as not looking at the road, texting, changing, etc.? Yes, the SHARP2 data set has multiple video channels that were recorded. There was the forward view. There's a view of the driver and a view of looking out the back window, or looking at the cab as well. So all of that data are in the data set as well. In terms of classification of what they were doing, some of that has been done, but I don't know that it's necessarily in the data set. I'll let Miguel respond to that.
Yeah, Lauren, thank you. So yeah, so I guess the video information to extract that, those measures is available. It has been completed for the crashes, near crashes, and then some sample periods of baseline, quote-unquote, normal driving. So for all those, that information has been cataloged. For everything else, if you're interested in other situations that were not a crash, near crash, or selected for baselines, then the reduction lab can be used to extract that information, or the secure data enclave can be used to get it.
Thanks, Miguel. Another question was asked as far as interaction with passengers. Due to the privacy of the passengers and the fact that they were not required, obviously, to sign waivers, there's not continuous video of the passenger compartment.
Right. Yes, that's correct. We have a blurred camera view, still shots that we're taking every so often throughout the trip, and so we can infer the presence of passengers. other than that, if the driver was having an active conversation with a passenger, we can usually tell that based on the driver view, because they tend to look at the passenger when they're interacting with them every so often. So we'll make that inference as possible. But same type of thing though. The video is available and it has been reduced for crashes, near crashes, and baseline.
Thanks, Miguel. Miguel, can you respond to Randy's question as far as the drivers and crashes there also?
Yeah, sure. So it doesn't necessarily imply that 50% of the participants were in a crash. A couple of things. One is some drivers have multiple crashes, and second is that the definition of a crash is available on the website. You can look at it and see what they decided was a crash, but it includes contact with anything on the roadway, and so that could include pretty simple and benign things such as curb strikes and things like that. The crashes are cataloged on based on the severity level, and there's 4 different levels of severity. And so level 4 would be those minor curb strikes that are relatively not they're not very severe. And so yeah, there's a lot of crashes, but you have to look at what the definition is. If you focus on level 1 and level 2, which are the more severe crashes, then that percentage drops way down. I also saw a question about the website for the webinar. We'll post the recording on the Insight website, so insight.sharp2nds.us.
Thanks, Miguel. There's another question there of what seems to be normal following behavior in terms of seconds of following distance. That's a relatively broad question. Miguel, do you want to try and address that generically, or do we have?
Yeah, I mean that was easy because we don't know. We haven't looked at it in those kinds of terms. I think that'd be an interesting research project though.
Also, from what I've done here, we seem to notice about 1.7 seconds, teens or adult, for time headway.
Thanks, James. Okay, last call for questions. Very good. Again, thank you very much. Hope you all have an enjoyable afternoon, and thank you for joining us. Joel, I'll let you take over and wrap things up as far as ending recording and shutting things down. Again, thank you all.